In this video, we're going to use double integrals with polar coordinates. Now, polar coordinates are very convenient if we are integrating over a circle or a semicircle or two circles, etc. And I'm not going to drive the equations. I'm just going to give them to you. In this video, we're primarily going to focus on examples. First of all, let's look back to what you had in Calc 2. Remember, polar coordinates were given like this. If you wanted to establish this point here in polar coordinates, it would be x was r cos theta, as you can see from the right angle trigonometry. Y equals r sine theta. And then r squared was x squared plus y squared. So we're going to use those when we make our conversions. So we're going to use these to convert our integrand to polar coordinates. And we're going to do that like this. And just remember, whenever we do this conversion, we're going to have to add the Jacobian, which is r. Again, I won't derive that here. In another video, I'll do that. So this is the equation we're going to use when we convert. And so we're just going to go directly to some examples. Let's take a look at this problem here. We're going to evaluate this double integral over dA. And sometimes this can say dA, which is more general, or it could say dx dy or dy dx, where R is the region in the semicircle of radius 3 that lies above the x-axis. So it would look something like this would be our domain over which we're integrating. Now, remember, of course, if you have a circle centered at the origin, the equation in polar coordinates for that circle is simply the radius. In other words, the equation for this circle in polar is going to be r equal 3. That's one thing that makes it really nice when you have a circle, a semicircle, etc. And if it's centered at the origin, the equation of the circle is very easy to write in polar coordinates. So let's take a look at our solution. And so again, this is the domain. And we're going to convert this to polar coordinates. So again, let's use our substitutions. Since we have an x squared plus y squared, we'll put in r squared for those. And as I said before, you always have to include that Jacobian with which is another r. Like this. So I replace the x squared plus y squared with r squared, still to the 7th. Again, you'll always include the Jacobian, the r, like this. Now we want to try to find the bounds. So now the way I picked here, I'm going to do r first when we do the integral. And so what I suggest, now on these easier problems, it's not necessary, but what I'm going to suggest is, so if we do r first, start with your inner surface. Now, in this case, there is no inner surface, so start at 0 and make arrows in the positive r direction in your region. So, again, in this case, you're starting at 0. And again, once you understand this, you don't have to do this formally, but you can do it in your head. But this is something that will really help you when you get up to a more complicated integral. So just think of this and think, okay, wherever the arrows begin is going to be your lower bound. Like I said, there is no inner surface here, so the lower bound is going to start at r equals 0. And then where the arrows end will be the upper bound, which is r equal, and remember, what is this equation in polar coordinates? The equation of a circle of radius 3 in polar coordinates going to be r equals 3, like this. And then so we're going to go from r equals 0 to r equals 3. And the next thing we want to do is find out what values of theta are covered. And now that's pretty straightforward. Remember, we're measuring theta from the positive x-axis. So if we go see how much is covered, this is going to be like pi over 2 up here. Then it's going to be pi. In other words, we're going to be covering from 0, theta equals 0, to theta equals pi. And so now go ahead and just evaluate your integral. We're going to have to simplify this first. So this is going to give us r to the 14th when we multiply those. And then plus 1 here, that's going to be r to the 15th. Like this. Then we'll go ahead and integrate this. And again, integrating r to the 16 over 16. Then substitute your bounds. So this is going to be 3 to the 16th. And then the lower bound is going to be 0. So I'm going to just leave, and when you put 0 in there, you get 0. So I'm just going to leave that off. Then integrate with respect to theta. And when we put the lower bound once again, we're going to get 0. 3 to 16 over 16 pi, like this. So again, remember to put these arrows in your domain. And we'll see that in the next example, why that will be helpful to do that. And next, let's take a look at this problem. Evaluate this double integral, where D is the region, the fourth quadrant between the circles of radius 1 and 4, centered on the origin. So I drew a couple circles of approximately radius 1 and radius 4. And remember, in polar coordinates, again, a circle centered on the origin of radius 1, the equation for that circle would just be r equal 1. So this will be, so for this inner one here, r equal 1. And then for the outer circle, it'll be r equal 4. Now they just want the region between these two circles in the fourth quadrant. So it's going to be down here. In this area down here. And so this is the region over which we're going to integrate. And so we're going to go ahead and put our double integral down. Remember, we're originally starting with this. Again, the original one could have said dx dy or dy dx. This is just a more general dA. And again, converting, remember x squared plus y squared is r squared. And then remember always to add your Jacobian dr d theta, like this. And again, if you want to integrate over r first, put arrows in the positive r direction. So in other words, you're kind of starting from your inner function and go to your outer function. So your arrows will kind of go like this. You kind of imagine your arrows kind of, if you were to extend them, they would go back to the origin. So you can imagine them extending back to the origin like this, more or less. So again, we're writing that, putting the arrows in the positive R direction. In other words, the radius would be increasing going from the inward to the out. And wherever the arrows start will be your lower bound. In this case, it'll be R equal 1. And where the arrows end will be your upper bound, R equal 4, like this. And again, say to yourself, what would be the values of theta? What do we cover? Remember, theta is measured from over here. So this is going to be pi over 2 pi, 3 pi over 2 would be the starting point here. And then it's going to go up to theta equals pi. Excuse me, 2 pi. Like this. Of course, again, since we're measuring from the positive x-axis, you could have also made these bounds go in the other direction. You could think of them as starting at negative pi over 2 and going up to 0. That would be just as legitimate. Now, again, if you just want to learn how to set them up, you could stop here. But if we want to go ahead and evaluate this is going to require U substitution. Because remember, you use U substitution if something outside your function looks like a derivative of something inside the function. So the derivative of r squared is going to be 2r, which looks something like this. So if we use U substitution, we'll set U equal to r squared, and then that'll give us du equal to r dr, and then du over 2 is equal to r dr, like this. So we can make these for our U substitutions. And usually what I do when I'm doing the U substitution, I won't show the bound because we're going to eventually be converting back to r and theta. So again, for r squared, I put in U. Then for r dr, I'm putting du over 2. I'll keep the d theta there. Then, of course, when we integrate sine of u, that gives us what? A negative cos negative cos u, and there's a 2 there. And I'm going to convert back to our original coordinates. Again, we'll substitute the r's back in. And that's going to be negative cos u was r squared. And I'm going to bring the 1/2 out front. That'll make it just a little bit easier to work with. And then our bounds were r equal 1, r equal 4. Theta was, would we say, 3 pi over 2. Theta 2 pi. Let's say if you want to use the other bounds, that's fine. And when you substitute these in, it's going to give you 1/2. That's going to be negative cos of 4 squared. So we're going to have a negative, that's going to be a positive after we put our bounded, that'll be 16. I'm going to reverse these because I'll put the positive one here and the negative one here because that's going to end up being a positive. So we're going to do 1/2 cos 1 minus cos 16 d theta. Theta equals 3 pi over 2. Theta equals 2 pi. And then finally, we'll integrate with respect to theta. That just going to give us theta. And if we put those bounds in, and you could just write them simply as the difference here. I'm going to write it the long way so not to confuse anyone. But you could have easily just had this times this minus this in parentheses. But let me show you here. This and then this, these are both the same. This minus this is just going to be 1/2 cos 1 minus cos 16 pi over 2, like this. Now notice that last bound, if you had put negative pi over 2 to 0, you would have got the same answer because you would have had 0 over here and then negative of a negative pi over 2, which would have given you a pi over 2 here. So let's take a look at this integral from 0 to this radical and from negative 6 to 6 on the x. So in the y, we're going from 0 to this, on the x, negative 6 to 6. First of all, let's see what we have here. What does this mean? This means, let me put this down, the solution. This bound here is telling us it's going to go from y equals 0 to y equal 36 minus x squared, and then from x equal minus 6 to x equals 6. So let's take a look at that. So of course, this is y equals 0. And so let's see what this is. Let's kind of work this out till we end up having y equals 36 minus x squared. If we square both sides, we come up with this. And let's see if we rearrange this a little bit. Equals 36, and we can make that into 6 squared, huh? So this looks like a circle of radius 6. So that's what we have up here. Now, we just have the positive side. So in other words, if we were working in the other direction, we started with this circle and ended up with this. When we take the square root over here, we would have a positive and a negative, wouldn't we? But here we just have the positive part. So that's telling us this is just going to be the part above the x-axis. So that's going to be, so our picture, our domain is going to look something like this. Again, where this is going to be y equal the square root of 36 minus x squared, like this. And then on x, we're going from 6, excuse me, minus 6. This should be minus 6 down here. Minus 6 to 6. Like this. So that's going to be our domain. And again, remember in polar coordinates, you can write circles centered at the origin as r equals 6, where the 6 is just the radius. And so now let's convert our integral up here again. X squared plus y squared is just going to be r squared to the 7/2. And again, always put in your Jacobian r, dr, d theta, like this. And again, within your domain, put arrows in the positive r direction, kind of centered at the origin. Now, we don't have an inner function, so you want to just sort of center them at the origin. Again, by now, you may not even have to put these in. You probably know what it is that you're doing. So it's going to go from r equals 0 would be your lower bound. And the upper bound is where the arrows end, r equals 6. And then say to yourself, okay, what values of theta do we have? Again, starting here, theta is pi over 2 pi. So it goes from 0 theta to pi like this. And like I said, this one we were just going to set up in polar coordinates, but this looks like this might not be too difficult to solve. And this is going to be what the 2's will cancel, so this is going to be r to the 7th. We multiply these, and then plus 1 r to the 8th. And when we do this, we'll have r to the 9th over 9 from 0 to 6. This will be 6 to the 9th. Integrate again, we'll get theta. Then we put the bounds in. That'll be 6 to the 9th over 9 pi minus 0, which is be pi like that. Next, let's take a look at this problem. Set this up in polar coordinates. So let's see what we have. Again, we'll just set it up because I think you know how to integrate it at this point. And once again, let's think of what we have here. Our bounds are really saying x equal minus 3 to x equals 0. And y is from minus this radical up to this. Because remember, the inner one is y, outer one is x. And so once again, let's focus on this. If we're to square both sides, we get y squared is 9 minus x squared, and then x squared plus y squared is 9, or 3 squared. So once again, the circle of radius 3. But now we're gonna have to see exactly what we have. Once again, notice if we work backwards, we have the negative part of this. So that's gonna be the part that's below the x-axis. We have something like this. And again, remember, if you were to put these in rectangular coordinates, this upper part would be y equal the positive 9 minus x squared. What's below the axis would be y equals negative that radical. And so we're going to be working with this lower part here where y is negative. But then also from this part over here, we're going from negative 3 on x just up to 0. So that's telling us we're going to be in this lower part, but we're only going to go from negative 3 to 0. So we're going to be in this region here, like this. And let's see if that makes sense. If we had originally set up this integral in x and y coordinates, we would have put arrows in the positive y direction and gone from the lower bound, which is this down here. I probably should have wrote this on this side, but you can see this is still established over here, like this. So we're going to go from here to 0 on the y, to y equals 0. And then on x, we're going to go from negative 3 to 0. So that makes sense. So it makes sense it's going to be this region here. But again, when we convert it to polar coordinates, we'll put arrows in the positive r direction. So then our integral now will be e, again, r squared here. And I always remember put the Jacobian in, r dr d theta. And from r equals 0, and would we say this was a circle of radius 3? So remember, in polar coordinates, this circle is represented as r equals 3. That's the equation for the circle. R equals 0 is the lower bound. The upper bound is r equals 3. And then were we starting? Remember, we measured the theta from the positive x-axis. We're starting at pi to 3 pi over 2. kind of messy. Let me put the answer in brackets here like this. So r equals 0 to r equals 3, pi to 3 pi over 2, and that's our integrand. And now I won't work it out, but again, if you use a u substitution, will allow you to integrate this, make u equal r squared, and then du over 2 will be r dr, and you can integrate like that.